Hi, my name is Thujan Mahesh Trivedi. In this presentation, I'm going to be discussing a popular type of design pattern called dependency injection. Design patterns. First, let me glance briefly over design patterns in general. So what are design patterns? After all, it makes all the talk in the industry, and architects and software engineers surely love to use them. Without going into the crux of the subject matter, design patterns, simply put, are a way of organizing the software code solution towards solving a business requirement and at the same time ensuring its due extensibility and maintainability even from a feature enhancement perspective. The design software solution should serve as a generic, reusable approach towards solving a similar problem with an intended goal. Design patterns are considered while architecting the software solution. Design patterns are supposed to be language agnostic, as the common theme or the generic solution must be transferable to any language the software is destined to be developed in. One must be careful to understand that design patterns are not idioms, although more often than not, idioms are misinterpreted as a design pattern. Idioms are low level design principles and they focus on implementation specific problems, often in a programming language, rather than the general structural principles of design patterns. Broadly speaking, design patterns can be classified into three main categories, namely creational, structural, and behavioral. Creational patterns provide object creational capabilities conforming to a business requirement in a rather controlled way. Structural patterns organize classes and objects to form large structures with varying functionalities. Behavioral patterns focus on identifying the communication between objects and relation between them. Following figure from Deepak Kamboj's blog shows a rather neat word cloud of various design patterns. Look closely and try to identify some of the popular design patterns that you might have already seen or used before. Do you see any such here in the word cloud? We can easily observe certain design patterns like abstract factory, adapter, decorator, observer, etc. in here, which Dr. K had covered during previous week's module. Without detouring enough, let me take a segue into first talking about inversion of control. Be rest assured, this will build up on the upcoming topic of discussion. In a traditional program development sense, we usually have an entry point for program commonly called the main function. All the business logic is implemented here, obviously with the help of several methods and helper functions. Thus, the custom code relies on helper methods and libraries, and the flow of execution flows in such a manner. This programming paradigm is also commonly referred to as procedural programming, focusing on all aspects of end-to-end. One of the harshest critics to this approach and a sleeker solution as well is given by the inversion principle. The flow is literally inverted. The custom code is now called from within the framework rather than the other way around. Event-driven programming is a popular application of this principle. Consider UI framework wherein framework takes care and sets up all the nitty-gritties required for functioning of the application. The software solution leveraging the framework has to only take care of the interactions amongst the elements through events, which are supported by the framework. Thus, the custom code only has to focus on its prime objective without worrying about the side tasks that go along with it. Phew, this surely takes off the load, huh? At this point, I would like to introduce the dependency injection principle. It simply asks us to decouple the dependencies among the high and low level layers in the software solution using frameworks usually. Coming back to the topic of discussion, let me introduce dependency injection in layman's term. It simply asks us to focus on the objective and not the side tasks that are part of the setup process. This can be explained through the following example. As a working software engineer, I have to drive to work every day. The main objective here is for me to reach the office and focus on my deliverables of software development. Driving to work is just a precursor to it, which sets me up to work from the office. Hence, it would be better use of my time and energy to simply take an Uber or a cab instead of driving to work myself. In this way, I am getting to office without explicitly doing the work for driving up there. I would like to reference the popular analogy with John Munch presented as a means to explain dependency injection to your 5-year-old kid. When you go and get things out of the refrigerator for yourself, you can cause problems. You might leave the door open. You might get something mommy or daddy don't want you to have. You might even be looking for something we don't even have or which has expired. What you should be doing is stating a need. I need something to drink with lunch, and then we'll make sure you have something when you sit down to eat. In the object-oriented programming paradigm, we rely on data through objects. These objects in turn would require and would be dependent on other objects, meaning they have dependencies on some other objects. The decoupling principle expects the class to focus on its main functionality, usually the business logic. As a result, the class should directly get all its dependencies handed to it directly rather than creating them. This ensures a loose coupling between the object and its dependency, thereby achieving higher flexibility, extensibility, and manageability for the core solution. The three main rules are well separated, and each component focuses on its prime objective in such a design pattern. The adjoining architecture shows the above principle in action, where a proper separation of concern is ensured. The typical architecture consists of a service providing the necessary functionality, which is in turn consumed by the client. The design pattern calls for an injector who is responsible for constructing the service and injecting into the respective client to ensure all its dependencies are received properly. Notice how the client relies on the interface of the service. This will become more clear as we dig into the specific implementation guidelines for dependency injection. Dependency injection is indeed a form of inversion control that we had visited earlier. At this point, I would like you to pause and think for a moment about possible ways to achieve dependency injection. Also think if there are multiple ways of achieving this, and can you think of any? We have already hinted toward one of the possible ways of doing it in the previous slide. Feel free to go back and look for the same. Take a minute and get back here to proceed further. So did you figure it out? If you think it can be done in multiple ways, then you guessed it right. Broadly speaking, dependency injection can be achieved in three ways via constructor injection, setter injection, and interface injection. We'll explore each approach. Before that, I would like to draw your attention to the following example of a client using a service without dependency injection. Notice how the service attribute is initialized in the client's constructor and fixated to a particular service. Any associated method will now use the initialized service property object as dependency as shown in the helper method. With constructor injection, we'd like to remove the creation and assignment of dependent service objects in the client's constructor. This fixed rigidity is not desirable. Constructor injection leverages the object-oriented programming flexibility of parameterized constructor to break this linkage dependency. As seen in the adjoining example, client's constructor receives all the necessary service objects as parameters to the constructor. These objects are then used to instantiate the service object properties in the client class. Thus, the past service dependencies will be used by the client, now using the above approach of constructor injection. We can also include validation checks for the constructor parameters for service objects to ensure they are not null references as shown in the example. Also, the client service dependency is loosely coupled now. It is still tied down to a particular service object as passed in the parameterized constructor. Due to this rigidity, the dependency cannot be reinitialized at runtime to some other object. Setter injection. Setter injection uses setter methods which are commonly found in object-oriented programming. We now have an independent setter method for each service object dependency property in the client class. Instead of using the constructor to set the dependency reference objects, we'll now use the respective setter method. This removes the rigidity of client service property tied down to a particular service object reference, as the setter method can be called during runtime to set a new service object reference as shown in the example. This improves flexibility of the setter injection implementation. One major critique and drawback for setter injection is that it becomes overwhelming and difficult to track service dependencies. It is easy to miss out calling the setter method for service property of the client class during runtime and thereby failing for null reference during program execution. Recall that final approach, interface injection, is indeed the one we had already seen in the dependency injection architecture diagram on slide 6 using interfaces. In this approach, the client relies on the interface of the corresponding service rather than directly calling the service. The service implementation always follows the agreement as defined in the interface. Hence, the client has to stick to this interface in order to call and use the service in its code execution. Setter methods are still used to dynamically assign the corresponding service dependencies as before. But here the service injector assigns the corresponding service dependencies by using service setter interface for all its clients. The fact that setter methods now use interfaces make this highly decoupled and flexible at the same time. We have gone through the inversion of principle and look closely at dependency injection pattern from this principle. We have seen three specific ways of implementing dependency injection. It is now a good time to discuss its merits and demerits so as to understand the motivation and benefits of using this design pattern. Dependency injection does surely provide improved flexibility, decoupling and separation of concerns along with a provision for concurrent code development. By leveraging interface injection, developers can work on two different classes at the same time, which have dependencies on each other, as long as they know the interface through which the classes communicate. Several third-party plugins and frameworks are available that assist in this process. Disadvantages of this design pattern is the added overhead of maintaining the configuration needed for clients in order to receive service dependencies. The separation of concerns from the perspective of separation of behavior from construction makes it difficult to trace code. Links and mappings between services and clients need to be maintained. Often such patterns, when incorporated, are framework dependent in order to achieve the necessary linkage. Popular frameworks like Spring, Weld, etc. can be used for this purpose. As an optional but highly recommended reading, I would like to refer interested audience to the popular blog post on inversion of control containers and dependency injection pattern by Martin Fowler. The final section on comparison between service locator and dependency injection is highly recommended. I would like to thank you all for attending this short presentation on dependency injection design pattern, and I hope it was informative and enjoyable. Thank you.